Hi and welcome to the first lecture on calculus. The lecture today is going to be about tangent line and velocity. You write the title here. Calculus has two main preoccupations. Let's go ahead and quickly review these things before we go into some examples. So we have two main topics in calculus. One of them, roughly speaking, asks the following question: how fast does something happen? Question number two that we are going to be preoccupied with is what is the total? I'll go ahead and explain this in context of several examples, but during the first 2 months of the class we are going to be working on just this issue: how fast does something happen? The technical word for this is differentiation. During the last month and a half in the course we are going to talk about adding things up and the technical title for that is integration. Okay, let's go ahead and just concentrate today on the first question itself. We go ahead and take an issue of how fast does a curve rise. Let's set this item A and set this item B here. Well, if your curve is a simple one, meaning a straight line, you have learned in college algebra how to handle that. Suppose I draw a straight line here, my X and Y coordinate axis, and say I have a line excuse me. So here I have a line, and if you ask how fast does it go up, we have a simple way of answering that question. Just pick 2 points on it, any 2 points you want, and find out the horizontal displacement from one to the other. Draw this rectangle here. Here's this one. Well, to go from this point to that point, you have a horizontal displacement that you call the run, and you have a vertical displacement that you call the rise. The ratio of rise to run is what you define as your slope. So your slope is rise to run. And the important thing about the straight line is that it doesn't matter which 2 points on this line you choose to figure out this ratio. If I chosen this point and this point, the ratio of rise to run for that would be same as it is here because of similarity of the triangles. Okay, well, calculus is going to be involved with a more complicated situation. What if we didn't have a straight line? What if it actually had a curve in it? So let's go ahead look at this question a bit more seriously now. Suppose I have a curve here, and I ask the same question: how fast does it rise? Well, you say, well, look, around here is rising kind of fast, around here is rising kind of slow. So the speed at which it is rising, is changing as you're moving from one point to another point. And that's what's going to make the situation complicated. So our first line of attack is to say, well, let's go for a familiar situation. Go back to that kind of a situation. Just pick 2 points here. I pick one point here, and say another point here. And I ask, from this point to that point, how fast did I rise? It doesn't matter how you came up here. Eventually you went from here to that point. So I go ahead and draw a straight line between the two of them. Okay, you want to find how fast you went up from here to here. Just measure the slope of this line. Figure out the rise and the run, divide them, and you get the slope. But then you come back and object that this is too crude of an answer. We want to know how fast we are going up moment to moment. This is from this point all the way to that point. What if I want to know the speed at which I'm rising right here? Okay, now we'll be opening a big can of worms when we insist on that question. Let's approach it slowly. I say, okay, let's make a compromise. I'll come a little bit closer, like here. To figure out how fast you went up from this point to that point, you can connect these two. And I say, well, go ahead and measure the slope of this line, and then you would know how fast you're going up from this point to that point. Again, you come back and insist, I don't want to go from here all the way there. I want to know right here how fast I go. Well, I keep playing the same game with you, and I say, okay, let's make another compromise. I come halfway to meet you. I come here. And again, I say, connect this point to that point, and draw your straight line, and see how fast that line goes up. The slope of that line is going to be the degree at which you are going up from this point to that point. Hopefully by that time an idea comes up to your mind that if you really want to know what is happening right here, just keep repeating this process. Keep coming closer and closer to this starting point, and you will see these lines that you are drawing, all of them bunching up closer and closer to a certain line. The slope of that line is going to be the speed that you're looking for, and that's going to be your answer. Well, what is that line going to look like? It's going to be a bit problematic. As this point comes closer to that, it's going to be hard to see exactly what we are doing, but you get the idea. This green line, and then that orange one, and this whatever color this one is, the purple one, they are all coming close to a so-called tangent line that sits right here. So this final line here is called the tangent line. All these other lines that we had, these are called secant lines. Secant line connects 2 points of a curve. Tangent line is what happens when one of these points comes infinitely closer to the other one. At the very end limit of this activity, you get something that's called the tangent line. So if you are satisfied with finding the slope going from one point to another point that's far away from it, idea of slope that you had in college algebra would be enough. You just have a secant line, you find the slope of that, and then you are done. But if you insist on knowing what's happening right close to a certain point, then you will be pushed toward the idea of a tangent line, and that's going to be beginning of course in calculus. So we are finding out how fast does something happen right at the point where it gets started. That gives us the idea of a limit. So the third item for this lecture is the concept of limit. Roughly, the process we went through here is a process of taking a limit. We are sending this point closer to that one, and at the limit all these lines bunch up close to a certain line. Our limit line is just this tangent line, and the slope of that tangent line is the limit of slopes of these secant line. Concept of limit is going to be a bit hard to digest in its full rigor. We are going to try to break it up to small steps and understanding little by little, and hopefully by the end of this semester you will be equipped with a basic understanding of what the limit is. Okay, to make sure that we understand how to do these things in a context of a concrete problem, I go ahead and pick an example and try to explain it for you. So here's a question. Find the equation of the tangent line to graph of say y is equal to x squared plus x at say x equals 1. So what we want to do is to pick up a specific curve. So instead of this arbitrary blue curve over there, I have something here that's given to me. I have to analyze that. So this is going to replace our blue curve over there. At x equal to 1, it means that's the point I'm insisting on working at. I'll be at that point x equal to 1 on this picture, and what I want to find out is the equation of that gray line over there. What's the tangent line? Now, many of you have taken the calculus course in high school, and probably your mind jumps to certain formulas that you have learned, and you want to use them in answer this question in like 5 seconds or such. That's all fine. We are going to have time for applying formulas that you know later on, but right now we want to know what is involved. So we are looking under the hood, looking at the situation in detail, trying to understand the process, and not just to display our knowledge of various formulas. So if you know those formulas, just put it outside of your mind for a while, and let's go through the process and then come back to those things later on. Now, we don't really need to have a detailed picture of this function before we get started, but it helps to have a reasonable setup. So let me go ahead and draw something halfway decent. So here, say my y-axis, and say I have my x-axis here. Let's mark this off at say this is 1 and say 2, and so at 1 location is 2. 1 squared plus 1 makes 2. At 0, of course, I'm at 0. At 2, I'm already extending the size of my page to 4 and 6. Maybe I use a different color so that here. At 2, I'm around here. 2 squared plus 2 makes 6. How about for some negative numbers? At -1, I make it 0. So that's another x-intercept. At -2, I will be at, well, that's going to be 4 minus 2. That's going to be 2. -3. 9 minus 3, I'll get 6. So, well, do you know what the name of this shape is? I'm sure most of you know. Let's see if I can draw it. I'm drawing things while not being able to look at my hand while drawing it, so the pictures don't come out not that great. I hope we get that fixed later on with better software and hardware, but let's live with this thing for now. Now, so here was my center, 0 here, 1 and 2, and of course this is 1 and 2 and so on. This was 6 all the way up here. So this is the graph of this function, and this is x equal to 1. We want to know how fast we are going up right at this point. If you do a very accurate graphing on a graph paper, you can actually tell what the answer is going to be by just looking at this thing, holding a ruler to it, and guessing the answer. But of course, we want to do it from by using algebra. Okay, let's go ahead and do the game we were playing here. What is the game? The game is to take a limit, go far away, figure out the answer based on stuff you know from college algebra, and then graduate to calculus and say, okay, let's take a limit. Let's just repeat these things and come close, see what happens. So I might as well go ahead and say I pick up, say, this point. So if I drew a straight line from this point to that point, almost coinciding with my curve right now, let me move away from it a bit. What would be the slope of that line? How would you measure that slope? Remember, slope was a ratio of rise to run. How do you figure that out? So this is the rise, this is the run. So here you say rise over run. Well, how would you figure it out in this case? If this is the end point here at 2, you'll be at 6. How did you figure it out? 2 squared plus 2 makes 6. So rise is from the distance between this point here and this point here. That is the rise. So what should I do? Take this 6 and 2 and subtract them. So rise is 6 minus 2. That's 6 minus this 2. Run is this one. It's just 2 minus 1. So that 2 minus 1, that gives us the run. And this turns out to be just 4 over 1, and that's just 4. So from here to here, slope is 4. Now, if remember, we are repeating this game. Pick point in between, figure out the slope, figure out another slope here, and so on, and try to guess where they are headed. You notice that's going to be a lot of work. We have to do another point, like pick this point, pick halfway point here, figure out where the height is going to be, and find the slope from there. Well, to cut through a lot of arithmetic, we are going to introduce a bit of algebra that's going to do all of these lines all simultaneously instead of doing one by one. First time around, perhaps if you haven't seen this topic, I advise you to go actually spend half an hour and try to get this answer by figuring out lots of these slopes and seeing where they tend. But one intention of calculus is to do things quickly. And so what we are going to do now is that I'm going to pick some arbitrary x anywhere on this x-axis. I'm going to call this whatever I'm picking here, just call it it's an x. It's a variable. I can choose whatever I want. At x, so don't start to think that x is 1.5 or anything. It's just some arbitrary point on this line. X is some arbitrary point here. I'll go ahead and find out what the slope is going to be if that point is connected to my startup point. What should I do? So here is the slope. Again, I write. Play the same game as before. I have to find this rise now. What did I do when I was dealing with 2? I figured out the height here by plugging 2 in the formula, figuring the height and subtracting the height at the beginning. So when I have x, I plug it in this formula, which is exactly what you see here. That's the height, x squared plus x. And the height at the beginning is 2. I have to subtract that, minus 2. So this minus 2 is just like same as that minus 2 over there. Instead of 6, I have x squared plus x because I am using some arbitrary point on the x-axis. Okay, now you think about this one. What is the run now? You're looking at this as your run. What is the run? You're going from 1 to x. So your run is what? If you wish, pause for a moment, try to answer the question, and then come back here. Again, my question is, what's the run if you go from 1 to x? You'll see, you'll hear me constantly asking you questions, and I'd like to see you try to actually answer them. You'll have to pause the video, answer, and come back and see if your answer is correct. That way you'll understand the situation a lot better than just listening. Okay, well, that answer turns out to be the difference of these two, x minus 1 is the run. So if I pick an arbitrary point here and find a slope from this line to that, find a slope from that point to the startup point, I'm going to get this expression. Now comes up the following question. We want to know the slope when x is equal to 1. Your tendency might be, let me go ahead and just use that in this expression. So you ask the following question: would it be okay? What happens to slope when x is just 1? Well, go ahead and put 1 here. Let's see what happens. 1 squared plus 1 minus 2 over 1 minus 1. What is that? 2 minus 2, 1 minus 1. And what is that? 0 over 0. Okay, you could say the first half of calculus is an attempt in understanding what is this thing, 0 over 0. It doesn't make any sense at all. There is no meaning you can attach to 0 over 0, and for that reason you cannot go ahead and just figure out the slope by choosing the first and last point to be exactly the same. That would be like this. Suppose I tell you, here's my starting point and here's my ending point, right? Same as the starting point. Now you tell me what's the slope of the line that goes through it. So all sorts of line goes through it. These are all lines that go through. If you choose 2 points to be exactly the same, infinitely many lines go through it. Slope of any of them could be a candidate. So this picture is not going to help us at all. We cannot choose the first and last point to be the same. And that is where all the difficulty is. we want that to come very close to the first point but not be same as the first point. That opens a huge can of worms. It also is a philosophical question. What do you mean something is infinitely close to another one but not being same as the other one? That's what we try to understand here. So what happens to the slope when x becomes equal to 1? This is meaningless. Zero over 0 is a meaningless expression. So what do you do instead? Instead we say we are going to take a limit take the limit of x squared plus x minus 2 over x minus 1 as x approaches 1. Once again, this is a type of a phrase you need to understand. You're going to hear sentences like this over and over again. Taking a limit of an expression when the variable in that expression approaches some number. What does that mean? Well, physically it means something like this. As this point comes close to this, that's like similar to saying as x comes close to 1. The slope of these lines approach a certain number, and that is what this one is trying to capture. This is a slope. It's going to approach a certain number when x approaches 1. Now how do you find that limit? It depends on the problem. Some problems are easy like this one. Some problems later on are going to take quite a bit of work to figure out what the limit is. So we are going to spend a substantial amount of time learning all sorts of tricks of the trade, figuring out the limits of various expressions. The expression that we deal with most often, but not always, are of this nature. 0 over 0 when your variable is pushed to be exactly like its limiting value. At least those are the more interesting examples. There's going to be some other examples, mostly for educational regions, that are just cooked up. Might not have same flavor as this. This is the most important type of an example we are going to see. Okay. Here, something nice happens that makes our job easy. Here, let's take x squared plus x minus 2 over x minus 1. I noticed from my knowledge from college algebra that I could actually factor this item in the numerator. Again, pause this for a second, tell me what the factorization is, and come back. Okay. Did you guess what the factorization is? Factorization is x minus 1 times x plus 2. And we have still that x minus 1 in the denominator. So long as x is a number other than 1, this fraction makes sense. And if that is the case, then you can go ahead and cancel these two. When you cancel these two, you get the answer x plus 2. So that is when x is different from 1. If x was the same as 1, this doesn't make any sense at all. This guy does. So they have nothing to do with each other. This is nonsense. That is sense. You cannot connect these two. When x is different from 1, you can say this is same as that. Okay. Now, when you want to take a limit of this expression, here is a shorthand we are going to use. Instead of full word limit, we write lim, x squared plus x minus 2 over x minus 1. And then to abbreviate all of this, x approaches 1, we write it like this. We write x approaches, here's the arrow, to 1. Okay, this is what you want to do. This expression is same as this so long as x is different from 1. So I go ahead and write that one. So limit of x plus 2 as x is approaching 1. So now this one is easy to guess what the answer is going to be. If x is very close to number 1, what is x plus 2 close to? Okay, again the question is, when x is very close to number 1, what is x plus 2 close to? You can pause for a moment and then come back. It's a very simple question. When x is very close to 1, what is x plus 2 very close to? And that is, the answer is, of course, 3. X is very close to 1. You're essentially adding something a bit shy of 1 to 2. So it's going to be a bit shy of 3. The answer is hovering around 3 and getting closer and closer to it. So here we use the arrow, over there we use the equal sign to say the number approaches that. So what we found out, here's our holy grail, that at the limit when x comes very close to 1, this line that now is a tangent line has a slope 3. You remember at the very beginning the slope was 4, our start of our experimentation. As you come very close to that point, the slope becomes 3. So here's a tangent line. Tangent line, slope of that is equal to 3. Now I'm almost done. I have this point. This is a point on the graph. Its coordinates are 1 and 2. I'm drawing a line with slope 3 at that point. What's the equation of that line? This one you remember from college algebra. Let me remind you. Equation of line with slope m through point AB is, what's that? Y minus the y of a given point is equal to the slope times x minus the x of the given point. That's essentially just the definition of slope. So here's a review item from college algebra. We need this thing very often. You get to know it very well. So application of that here is that I write y minus the y of a given point. What is the y of a given point? Let's go back here. Point here is point 1, 2. Y of a given point is 2. Y minus 2 is equal to, slope is 3. And x of a given point was just 1. So again, 1 was given, x approaches 1. This is what we got from our equation, original equation that was given to us. X squared plus x. When x became 1, y became 2. That's the 2 that I'm using there. And 3 is the slope that we worked so hard to get. Okay, so that becomes the answer. This is the equation of the tangent line. Sometimes you get to write your answer in one of a variety of formats. And this course is not about what type of formula you want me to write. Rather, it's about understanding all those formulas are talking about the same thing. So if you want to take this thing, change it into that format, and then rewrite this thing in this format, that is all fine. There are different names for these formats. It's called the point slope form. This is called slope intercept form. So here slope is 3, intercept is -1. What intercept are you talking about? If you continue the tangent line, has a slope of 3, and its y-intercept is going to be -1, as we just discovered. So we found the equation of tangent line. Well, let's go ahead before we go into another example. Just remind ourselves that we are dealing with very excuse me very important topic here that is widely applicable to all sorts of situations. Let me remind you of some equivalent phrases that people use when they are really doing the same thing that we are doing here. These slopes that we find, sometimes people refer to it as a speed. This idea that we have of dividing one quantity by another quantity and getting something that we call a slope is a concept that gets to be used in so many different situations. Well, one situation that you are very familiar with is the concept of speed. What is speed? Speed is a ratio of distance traveled, so distance traveled or displacement divided by time. Distance you travel divided by time. It's a bit more correct if instead of distance we say displacement, but that might sound a little bit too unfamiliar to you. Displacement divided by length of time it took for the trip. So if you go on a trip and you go 100 miles and it takes 2 hours, you say you traveled at the speed of 15 miles per hour. So this speed is really a ratio that is obtained in a manner similar to the way we obtained slope. We are going to do another problem related to this. Sometimes people talk about the rate. Rate is rate of change of one quantity. So typically this is change in a quantity usually in the denominator you have change in time. Suppose you are watching the price of gas and you notice that during some turbulent times the price of gas went up by 75 cents in a manner of just 5 days. Something happened, maybe a hurricane or something, and the price went all the way up. When you take this ratio, I report the ratio as a rate of increase of 15 cents per day. So the idea of measuring a change divided by some other change is very common. Again, let me remind you, this concept of change is same as the concept of rise and run. Here, when we go from one point to another point, you have a change in height. Change in height, you call it rise. change in horizontal location, you call it run. So it's a ratio of one change divided by another change. Okay, what other concepts you have in everyday life that is somewhat similar to this? Let me think. Perhaps you are doing any carpentry job. You have the concept of a pitch. Well, I wouldn't be pitching an idea to you that calculus is necessary for carpentry, but idea of a pitch is exactly the same thing. It's a ratio of rise to run. So if you're building a roof or something and you're going up by 3 feet, when you are going horizontally by 4 feet, you're going to say you have a pitch of 3/4 or something like that. I hope I'm correct on that. If somebody has worked for a roofing agency and you find out that I'm not using the phrase correctly, let me know. Other kind of phrases people use that are somewhat similar to this, you use the notion of a grade. Sometimes people who are working for highway department use the concept of grade. You might see signs on roads next to mountains and such advising people to use a low gear because the road has a high grade. What does a grade mean? If you have a road going up like this, you want to tell people to use low gear so that you can actually go and not get stuck in the middle of the road. Typical way of measuring the grade is to figure out how high you go for 1 unit of horizontal displacement. So it's exactly ratio of this quantity to this quantity, the same as the slope. So if the grade is like 5%, you want to give some advice to people maybe. Similar words, you talk about slant, you talk about incline, you talk about steepness. What else? Maybe you want to talk about tilt. And all of these ideas have something to do with the angle that you are making, so somehow they are all connected to angle that you make with the horizon. So if you remember from trigonometry, I hope you remember from trigonometry, the formula that connects this angle to the ratio of the opposite and adjacent side is, what is that? Let's call this thing rise. Let me call it rise. And well, that's not going to help because run also starts with R, so let me call it something else. Let's just call it, say, B and A, and here's my angle theta. What's the connection between these three objects? Three quantities. We really have tangent of theta is B over A. So tangent of the angle that the line makes with the horizon is same as the slope of that line. Tangent of the angle that the line makes with the horizontal axis is same as the slope of that line. So that's an important thing to keep in mind. Okay, now many problems you see in this section are related to finding velocity. Let's go ahead and now the algebra that is involved in this is exactly the same as what we have gone through. What is important is to understand the notation and the meaning of various variables. So suppose I tell you t is time measured in some units, say seconds or minutes or hours or whatever. So time is t. And now let me say y is going to be my displacement, or look, is a position, excuse me. Y is the position. So what do we have in mind we have an object traveling on this y-axis perhaps. Here's the y-axis, and some object, here's an object for me. So just an ant here starts to crawl maybe. So it's walking up this y-axis. And I go ahead and record his or her position at any time t. So I know where this object is at any time t, and or somebody else finds it and they tell me here's a connection between these two. So that's the start of the problem. These are given. The y is perhaps is equal to t squared plus t. I chose a kind of a formula similar to what we have done so that we don't duplicate all of our stuff all over again. So position of an object is given like this. Pause for a moment and try to understand what is involved here. If time is 0, what is the location of this object? Suppose here's time. If time is 0, location is also 0. If time is 1, what's the location? At 1 second, perhaps the object at this location. So these are the y values. Now if you want to have a convenient way of showing the t values as well, the best way to do it is to graph y versus t. So here I make my horizontal axis to be t. The object isn't traveling. Here is the object traveling over there. When t was 0, well, I'm here. When t is 1, let's go show that one. When t is 1, there's t is equal to 1. Really, the object is here. It has traveled from this point to that point. When t is equal to 2, let's pick t equal to 2. There's t equal to 2. When t is equal to 2, the object is the 2 squared plus 2, that is 6. 2, 4, 6. Again, my picture is. Now, a convenient way of showing what is happening is to graph y versus t. That is, I go ahead, find the point with coordinate 1 and 2. Find the point with coordinate 2 and 6. And graph this whole thing. So I'll have this particular picture. Now you might get confused. We are not saying anything is traveling on this curve. The object was traveling up a straight line. It's just going up this line. This one we did for our own convenience. We drew an axis for the t-axis so that we can show at any time what the position happens to be. Now let me ask you the following question. What is the average speed let me call it average velocity, so that's a more official average velocity, excuse me, between time t equals 1 and t equals 2. Let's go back to this picture to see what happened. At t equal to 1, the object was at position 2. T equal to 2, object is here, which is let's say 1 second and 2 seconds, and let's say 2 feet and 6 feet. So how much did the object get displaced by? It got displaced by 4 feet. Is that right? 6 minus 2 makes 4 feet. How long did it take for it to do that? Well, it took 1 second. Between 1 and 2, there's 1 second of time. In 1 second, it traveled 4 feet. So we say, here's what I do. At t equal to 1, y is equal to, I plug 1 here, 1 squared plus 1 is 2. At t equal to 2, y is 2 squared plus 2 makes 6. Say speed, again, I made the same mistake. Velocity, by the way, the difference between the speed and velocity is that the speed is the magnitude of velocity. There's no positive or negative associated with it. There's no sign associated with it, nor a direction associated with it. But right now it doesn't make that big of a difference. Velocity is displacement. Let's remind ourselves. Displacement divided by length of time. So that's the time passed. Displacement, we went from 2 to 6, so 6 minus 2. Time went from 1 to 2, 2 minus 1. So 4 over 1, and that is 4. What kind of velocity is this? This is something we call average velocity. From time t equal to 1 to time t equal to 2, average velocity is 4. What do you mean by average? Well, just like about anything, the speed changes as time passes by. Sometimes when you're on a highway you go fast, sometimes you go slow. If you want to figure out your average speed, you take the displacement and divide it by the length of time you have been on the highway. So what you are getting here is the average velocity. So now what if I ask you find the instantaneous velocity? At t equal to 1. What does that question mean? What is instantaneous? Well, sometimes you want to know what your speed is right now, not between that given moment and say a couple of hours later, but you want to know what is it right now. And what should we do? Well, in practice, what you have to do is to take a very, very small window of observation. Instead of going all the way from 1 to 2, to go from say t equal to 1 and to t equal to, just wait a very short amount of time, let's say 1/100th of a second. Figure out what y is at the beginning and figure out what y is supposed to be at this time 1.01. Figure out the rise, figure out the displacement, and figure out the length of time it took. Take the ratio and you get something close to instantaneous velocity. What if you really want to get closer to instantaneous velocity? Well, make the window of observation smaller. Wait just 1,000th of a second to do that. What if you want to do it better? Well, wait 10,000ths of a second to do better. And so you get the idea. If you wait a very short amount of time, then you get a better approximation to what your velocity was at that given moment. How can we cut through all this kind of calculation? Exactly the same thing that we did here. What did we do? We found out the displacement, we found out the length of time, we divided, took a limit, and that gave us the slope at that time. Now it's going to give us the velocity. So the algebra is exactly the same, it's just plenty of meaning is attached to it. So instantaneous velocity is equal to the limit of displacement divided by time as time, that means time passed. So this is the time that passed. As time passed approaches 0. So what is it in this problem? Instantaneous velocity is equal to the limit of displacement. What is the displacement? Let's go back here. This is the position. Tells us the position of the object at any time. At t equal to 1, the position is 2. At any arbitrary time, this is what the position is. So if I subtract them, I'll get the displacement from time equal to 1 second to that eventual time. So displacement here, t squared plus t, that is a position at time t, minus the position at the start time. At start time, t itself is 1, so 1 squared plus 1. Okay, once again, these are positions. When you subtract the positions, you get the displacement. Okay, how much of time has passed? You are starting to look at things at time equal to 1 second, and you are ending your observation at time t seconds. So time passed is t minus 1. As time passed approaches 0. What does that mean? It means your final time is very close to your startup time. Your t is very close to 1. Well, what is this thing? Let's write it again. Limit of t squared plus t minus 2 over t minus 1 as t approaches 1. Well, this is exactly the same as what we did here. Just change our letter from x to t to give it some meaning. The meaningless x was changed into time, but the process is exactly the same. So all of these type of activities we want to do in various applications are all covered by the concept of slope. So this is, we have already found, based on what we have done. Let's quickly remind ourselves, we could actually divide the numerator by denominator. That turned out to be just t plus 2. And when t went to 1, this whole thing approached 3. So what is the 3? 3 is the instantaneous velocity at that moment, at the moment t was equal to 1. Okay, this was a very important lecture. I hope that you go through these concepts several times and try to do as many problems as you can from this section. They might look a little bit tedious to you because well, yeah, lots of calculations are involved, but you have a calculator that helps you to cut through a lot of these bitty stuff. But do spend time on this to understand what is going on. That's going to be setting the foundation for a lot of other things coming up. Okay, so good luck and God bless. See you in the next lecture.